All right, ladies and gentlemen, this is Miss Kubasek, and I will be taking care of 7-2, exploring similar polygons. Before we get going, I have a math humor, and I want to go solo on this one. Question, what does the 0 say to the 8? Answer, nice belt. Yeah, that's not as funny if you have to do that by yourself, so maybe next time I'll get Flanagan on that. So, warm-up. I've got 2 questions for warm-up for you. One of them has to give the ratio in the simplest form, and the other one is just solving the proportion. How about you do me a favor, go ahead, solve both of those, pause the video, try to do it on your own, and then when you're all set and ready, I'll have the answers up for you. So let's go ahead and take a look at the first one. We have to give the ratio in the simplest form. So our ratio is 24x to 6x squared. And when you're simplifying, you're trying to get common factors. What do they have in common? So between 24 and 6, I notice that they share a 6. So if I pull a 6 out of 24, I'm left with 4. And a 6 out of 6, I'm left with a 1. Also, between x and x squared, these two share an x. So if I pull an x from this one, I don't have any x left over. And if I pull an x from this one, I'm left with x. So our ratio in simplest form is 4 to x. When you solve a proportion, what we're going to do here is we're going to cross multiply. So we've cross multiplied, and then I distribute my 2 through and my 8. Once I do that, I get my x's on one side, and then I go ahead and I add the 24 to the other. So when I solve and I'm all set and ready, I end up getting x equals 9. So for our notes today, what we're going to do is we're going to explore similar figures. And with similar figures, they are figures that have the same shape, but not necessarily the same size. So similar, remember when we first talked about congruent way back in first semester, we had a symbol for congruent, and it was an equal sign with a little squiggly above it. When we talk about similar, we're going to use this symbol. It's a little squiggly, and that just means similar. So if I'm talking about triangles like these two, triangle 1 and triangle 2. If we say that triangle 1 is similar to triangle 2, we say so shorthand by saying triangle 1, and then using the similar symbol is similar to triangle 2. Also, look at this. We've got triangle 1 and triangle 3. Notice they do not have the same shape, okay? So we would say, oh, triangle 1 is not similar to triangle 3, and to say not similar using the symbol, you just use the squiggly with a slash through it. So similar figures, same shape, but not necessarily the same exact size. Congruent figures have the same shape and the same size. So let's take a look at similar polygons. 2 polygons are similar if and only if their corresponding angles are congruent. So that means angles from one polygon to the other have to be congruent, and their corresponding sides are proportional. So if we take a look at an example, and I want to know, is polygon ABCD similar to polygon EFGH? So what we're going to do is we're going to take a look at the corresponding sides, okay? So if I'm looking at this, first off, what I'm going to do, which should have been done in my diagram, and that's my fault, I'm going to go ahead and I'm going to mark these angles. Angle A, we're going to make congruent to angle E. We'll make angle B congruent to angle F. C will make congruent to angle G, and just because it's getting harder for me to mark the angles, I'm going to make this one really funky, and we're going to say angle D and angle H are congruent. So those should have been marked prior to me starting. Sorry. So we want to know, are these 2 polygons similar? Well, the first step was we had to prove that corresponding angles were congruent, and we just did that. If they were marked as congruent corresponding, then yes, indeed, we've got half of the battle fought with similar polygons. The next thing we have to do is we have to make sure that the corresponding sides are proportional. So if we look, we notice that AB corresponds to EF just because of the way in which it's a letter. So AB corresponds to EF. So that means I would have, if I'm working with AB and I'm checking out the ratio there, AB to EF, that's 10 to 5. That's going to simplify down to 2 over 1. The next set, we're going to do this for all 4 sides. BC, if I take a look at BC to FG, yep, okay, BC to FG, BC was 8, FG was 4. This is why it's important for you to know how to simplify your ratios. So I get 2 over 1. Next, if I compare DC to HG, I have 6 over 3, that's 2 over 1. And take a look too, I'm always starting off with this polygon. Never am I jumping back and forth between which one am I starting with. The last side I have is AD, and we're going to go ahead and compare, and I'm going to write it up here, AD compared to EH. And I've got 5 over 2.5, and of course it simplifies to 2 over 1. So since each and every one of these ratios simplified down to the same exact value, we knew that ABCD of those sides were always proportional to the sides of EFGH. Since the angles were congruent and the sides were proportional, we knew that these two were indeed similar. So in this example, we're going to identify the pairs of congruent angles and corresponding sides. So we are indeed working with two similar figures. I should probably tell you that. And if you're not quite sure, you can always go through the test and make sure by showing that the angles, the corresponding angles are congruent and the corresponding sides are proportional. And if you look at it, MN, yep, corresponds to TQ, and they're in a ratio of 2 to 1. TR and MP, this is in a ratio of 2 to 1, and NP and QR are in a ratio of 2 to 1. So the ratios are fine for my corresponding sides, and my angles are indeed congruent. So if we're going to write down our pairs of congruent angles, I would say that angle M would be congruent to angle T. Angle N, the right angle on the first one, is congruent to angle Q. And angle P is congruent to angle R. So those are my corresponding angles. They're my congruent ones. And then we're going to go ahead and list the corresponding sides. So when I identify the pairs of congruent angles, you list them as congruent angles as I've done so. But when you're identifying the corresponding sides, let's go ahead and set up it as the ratios as what I was talking about. So if I start off with MN here, I would say MN corresponds to TQ in the other diagram. Then we know, since these are similar figures, the ratios have to be the same. So if I started off with MN to TQ, let's go NP to QR. So NP to QR. And then the last set would be MP to TR. So those are the listing of our congruent angles and corresponding sides. When we were talking about proving similar polygons, we ended up coming up with this ratio between, this number between our two figures. Well, that's considered the similarity ratio, and or we can even call it the scale factor, and that's the ratio of the lengths of the corresponding sides of our two similar polygons. Now, order is very important when you're talking about similarity ratio or scale factor. So I've got our two triangles here, ABC and EFD, or DEF. When you're talking about the similarity ratio from triangle ABC to triangle DEF, you would say, oh, it would be 3 to 6, or reduced down to 1/2. But if you switch this around, you start to talk about triangle DEF first to ABC, then that's going to change it up a little bit, and I have to start off with a side on this triangle first. So DE, we'd use 6. And then for AB, we'd use 3. So pay attention to the order in which you're writing these. Similarity ratio, whatever the triangles that you've written down first, that number goes on top, and then the triangle that you've written down second, that number goes on the bottom. So you might be getting these two different scale factors depending upon how you're stating your similarity ratio. In our example here, we're going to determine whether rectangle ABCD and rectangle EFGH are similar. And if so, we are going to write a similarity ratio and a similarity statement. So the first thing is, with similar polygons, you have to determine if the corresponding angles are congruent. In our case, the biggest piece of information is that they're giving us rectangles. So if we have rectangles, we know every single angle in these two polygons are right angles. So that means corresponding angles are indeed congruent. So that's half of what we needed to prove. The other half we need to work with is the corresponding sides. So if we're working with the corresponding sides, I would probably say that AB in the first rectangle corresponds to EF in the second rectangle. And AB has a measurement of 6, EF has a measurement of 4. If we reduce that by pulling 2 out of each, I get 3/2. The next set we're going to deal with is BC and FG. So we have to do this to make sure that corresponding sides are proportional. So BC was 9, and FG was 6. So we've got 9 over 6, take a 3 out of each, I'm left with 3 halves. You can continue to do this if you would like, CD to GH, and we know that CD should be 6 and GH should be 4 because they are rectangles, opposite sides are congruent. That'll reduce down to 3 halves, and if you would like to, you can finish it up and say that AD and EH are ratio. We're going to take similar. EH we say is 6 and AD is 9, and reducing that down I still get 3 halves. Since you ended up getting 3 halves for all of our ratios, we know that the similarity ratio is going to be 3 halves, and our similarity statement is that rectangle, since it's 3 halves, it's very important that you understand what rectangle you put down first. You are not going to put down rectangle EFGH first, because with these ratios, you're always starting off with rectangle ABCD. So rectangle ABCD is similar, that's supposed to be that squiggly, I know, it's kind of hard here, to rectangle, and that's a rectangle, EFGH. So you need 2 pieces of information, the similarity ratio, which was 3 halves in this case, and our similarity statement. So in this next example, what I would like for you to do is I want you to determine whether the polygons are similar. If so, you're going to write a similarity ratio and a similarity statement. If they are not, what I would like for you to do is go ahead and write down why. So take a minute, go ahead and pause the video at this point, do the problem, and then come back and we'll talk about it. All right, so let's take a look at these two. Now, you can't just say, oh, they're not similar because they don't look the same. We have to really prove that out, okay? So yes, your gut feeling might be saying, oh, you know what? These aren't similar because they're not the same shape. Well, why? Let's take a look. So the first thing we're going to look at is, let's go ahead and take a look at the sides, just because those seem to pop out at me. Yes, I've got 10 here, and yes, I've got 10 here. If we would say, yep, the corresponding sides then would be the 5 and 5, they would have a similar ratio of 10 to 5, which would represent 2 to 1. However, I don't have anything about PR and I don't have anything about SW, which kind of makes me a little leery. So I'll hold off on that fact, and let's go ahead and take a look at the angles. If I'm looking at the angles, we do have an isosceles triangle in both instances because we have 2 sides that are congruent. Well, let's take a look at the smaller one. If I look at this, I know that this is 62 degrees. We know in an isosceles triangle that base angles are congruent, meaning that this angle right here should also be 62 degrees. Now, 62 plus 62 gives us 124. And if I'm working with 124 degrees, we know 180 degrees make up a triangle. So you take 180 minus 124, I'm left with 56 degrees. But wait. If I look at it, and I look at the other triangle, it does not look like those corresponding angles are congruent. So, are these 2 triangles similar? We would say no. So at some point in time on this paper or note, you would want to say that triangle PQR is not similar to triangle STW since corresponding angles are not congruent. Not congruent. There we go. And that should be enough of an explanation. So instead of trying to prove if figures are similar, why don't we go ahead and say, you know what? These 2 triangles are indeed similar. And if they are similar, let's go ahead and figure out what the values for x and y are. Now, looking between our 2 triangles, I notice that they say that AB and EF pair with each other. So AB and EF pair with each other. So I know that if I write that down, AB and EF, it would be like saying 3 compared to x. Next, what about the next set? How about BC? BC and FG compare with each other. So let's say BC and FG. So we would have a 4 to a y. The last set that we're going to use would be AC and EG. And AC is 5, and when we compare that, AC is 5, we're going to compare that to our EG, and our EG was 8. Now, what we're going to notice is that out of these three ratios, or proportions that we really have set up now, 2 of them have variables, and 1 of them actually has a whole set of numbers. What I would like to do is, this is my scale factor. This is the scale factor from triangle ABC to triangle EFG. We're going to use this scale factor to help us solve individually for the x and the y. So the first thing I'm going to do is I'm going to take that 5/8, comparing the triangle ABC to triangle EFG. And we'll go ahead and say that 5/8, we'll compare that to the 3 over the x. So 3 over x. Now, when I solve the proportion, I cross multiply, I get 5x equals 24, meaning x equals 24/5. I can leave it like that. I like it, actually. Okay. Now, we're going to do the same thing. We're going to use the 5/8 this time, but instead of using the AB over EF ratio, we're going to use the BC over FG ratio, and that ratio was 4 over y. Cross multiply here, I get 5y equals 32. Divide, I get y is 32/5. For our last example here, we are going to use an actual racing car's measurement and a model of the racing car to determine the length of the racing car in the model, and we're going to use proportions to do that. So if I take a look at our model car, I want to know, what is this measurement for x, and how can I find that? Now, you've done this before in your previous algebra classes or pre-algebra, and I would like it if you would pause the video here and go ahead and try this out on your own, and when you start the video back up, I'll have my answer written down and I'll run you through it. So let's go ahead and take a look at how I set up my problem. If I started off with the length of the model car x, I wanted to compare that to the length of the racing car. And the length of the racing car was 5 meters, so that's why I put x over 5. Now, since I started off with a length from our model car, I'm going to go back to our model car and talk about its width. The width of the model car is 6.3, and we're going to compare that to the width of our actual racing car, which is 1.8. Once you set up your proportion, go ahead, cross multiply both sides, and I end up solving by dividing by 1.8. So the actual length of our model car is 17.5 centimeters. If you have any questions regarding what was covered in the video, make sure to ask in class. Otherwise, have a good night.